So let's get started. So this week we will be solving questions related to the transient heat conduction. So basically, I will solve some questions related to the lumped systems, and I will also devise few questions from FANS and the heat generation problems. So last week there was a couple of questions related to the heat generation in the adiabatic wall with the adiabatic one side of the plane slab. And so I will begin with the heat generation, and then I will move to fin, one or two question of fin, and then I will solve few problems related to the lump systems. And I will also solve one problem related to the semi-infinite body. And next week I will carry on few problems related to the semi-infinite body, long bodies, and all. And we'll start the convection part next week itself. So we can start with the simple true and false question. So the first question is related to the heat generation problem. So we need to identify the statement which is true and false. So the first statement says that in certain systems such as electric resistance heater, nuclear rod heat is generated within the conducting medium. As one might expect, the generation of energy within the conducting medium produces temperature profile different than those of simple conduction. So, is this statement is true or false? Hello.
Yes, sir.
Uh, did you see the first statement? Is it true? I mean, or false? My screen is visible, right?
Yes, yes.
Yeah. So the first statement actually says that if there is a heat generation within the body, then the temperature profile will be different when compared to the case when there is no heat generation.
That is true.
Yeah. So this is actually linked with the question that there was a question in the previous case. So let me extend this statement into that problem. So in the last class, we have seen the situation where is one's wall is insulated, and there is a heat generation within this plane slab, and the temperature variation of this plane slab was look like this. So there was a question that why it is not like this or something like this or this for the uh, for the case where the left side of the slab is adiabatic or there's no heat flux at the left side of the slab. So the main reason for this is since there is no heat transfer at the left side, the slope of the temperature gradient here will be zero. That means dt by dx equals zero, which ensures that the heat flux will be zero at the left hand side. And if there is a, let's imagine there is a finite slope at the left. Like this here, then the slope here is not zero. Slope in this part is non-zero, and according to the Fourier's law, it ensures that there is a heat flux at the left hand side also, and the heat generation in the plane slab is uniform. So there is no specific location of the heat generation. It is uniformly there in the entire plane slab. So to ensure there is no heat flux, the slope at the beginning should be zero, and there should be decrement in the temperature afterwards. So for the plane slab, the variation of the temperature with heat transfer, with heat generation, it depends on the boundary condition which we specify at point 1 and at point 2. And based on the boundary condition, the temperature gradient varies. So for case in the first case where the one side is insulated, we saw that the slope of the temperature profile look like the green line like this. But if the temperature at 1 and 2 is same and there is some heat transfer in both of the side, then it would be perfect symmetry. And if it is different, then there will be some asymmetry in the temperature profile. So basically we are solving the second order equation here, and we have a solution for this equation. And based on the boundary condition that we are putting from the conditions, we are getting different kind of a temperature variation in the slab with the heat generation case. So in all the cases, the variation of the temperature is actually depends on the distance x and the boundary condition. So we can move to the second part. Hello.
Yes, sir.
You have any question?
No, it is okay, sir.
Okay. So the next part of this question is: it is possible to increase the energy transfer between a surface and an adjacent fluid by increasing the amount of surface area in contact. This increase in area is accomplished by adding extended surfaces that may be in the form of fins or spines of various cross section. So is this statement is true or false?
Maybe so it is true because effectiveness cannot be always greater than 1.
Yeah, so in case of effectiveness greater than 1, this statement is true. And for if we introduce the fins and its effectiveness is less than 1, then definitely there is a reduction in the heat transfer when we add the fins.
Yes.
Yeah. So let's move to the next question. So next question is based on the heat generation. So we have solved some couple of problems in the previous class where we solved the second order equation. So it is similar to that one, just to revise the same thing. So according to the question, there is a semiconductor material with a thermal conductivity given, and we have given the electrical resistivity. The geometry of the cylinder rod is given 40 mm long and the diameter of 10 mm. And the longitudinal surface of a rod is well insulated and may be considered adiabatic, while the ends are maintained at temperature 100 and 0 degrees Celsius. If the rod carries a current of 10 ampere, what will be its midpoint temperature? So again, we need to solve the governing equation. So we have given the temperature and the dimension of the rod. So this is our equation. And when we integrate it, we will get now we need to apply the boundary conditions. So we have given the temperature at the both ends. That means we need to apply the constant temperature boundary condition at both the ends. So at first end, let's say the temperature is T0, which will give T0 equals C2 when we put x equal to 0 in the equation 1. And if we put x equal to L in equation 1, the temperature is, let's say, TL. So plus T0. So when we solve this, we will get C1 equals so this is my C1 and this is my C2. So I can plug in the question one, equation one. So we will get the temperature profile. As T minus T naught QL square 2K So this will be my temperature profile if I put the value of C1 and C2 here. So C2 is my T naught and C1 is my, let's say, equation A. So now we need to find the midpoint temperature at x equal to 0, x equal to L by 2. So it will be T minus T naught QL by, and we will put L by 2 here. So on further simplification, I can write this as so this is my temperature at x equal to L by 2. To find the Q, we have given resistivity and the current. So we will use this relation. So here I is the current, which is 10 ampere, and resistivity will be given by rho L. So rho is my 2 10 to the power minus 5 and L is 40 mm. So I'm writing in meters, and my volume is pi by 4 d square L. So from here we can get, if we just put the values of resistivity and the length, we will get the value of heat generation per watt per meter cube as 25.6, and we can just directly put here and substitute all the values here to get the temperature at the desired location. So in this question we have given the conductivity, resistivity, the geometric feature of the cylinder, and the surface temperature at the both ends, and we need to determine the temperature at the mid of the cylinder at x equals L by 2. So we solve the governing equation first, we integrate it, and after integrating we get the solution in terms of constant. Now since we have given the two temperatures at two ends of the cylinder, we apply the constant temperature boundary condition at the two end at x equal to 0 and x equals L, and then we determine the constant C1 and C2. Once we get the C1 and C2, we just put back into the equation 1 here, and we get the temperature profile like this after substituting the expression of C1 and C2. Then since we need to find the temperature at x equals L by 2, we need to substitute x L by 2 in this equation in the temperature profile to get the desired temperature at the desired location which is asked. So is it clear? Any doubts in this question?
No, sir.
Okay. So let's move to the next question. So next question is again true and false question. So it is based on lumped heat transfer. Uh, so the first statement is says that when a solid body is being heated by the hotter fluid surrounding it, heat is uh, first convected to the body and subsequently conducted within the body. The Dirac number is the ratio of internal resistance of a body to heat conduction to its external resistance to heat convection. So we can discuss about the Biot number part later after this. But is the remaining one is correct? Remaining statement is correct or incorrect as per you? That there is a system and there is a fluid, surrounding fluid, and it says that there is a hello.
Yes, sir.
So you are saying anything?
Yeah, this I think this is true because convective and conductive resistances we consider when we encounter these type of problems in heat exchanger.
Yeah, so the statement is true indeed. So when a solid body is there, placed in the convective fluid, which is and the fluid is more has a higher temperature than the body, then there will be a convection heat transfer to the body. And once the surface temperature of the body rises, then there will be the conduction heat transfer within the body. So the statement is true, and therefore we need to consider the two resistance here. One is the resistance from the convection and one resistance from the conduction, and Biot number is the ratio of these resistance that we will discuss. So the second statement is the lump system analysis assumes a uniform temperature distribution throughout the body, which is the case only when thermal resistance of the body to heat conduction is zero. Thus, lumped system analysis is exact when Biot number equals zero and approximate when Biot number is greater than zero. Is it true statement? So again, you can ignore this, the last statement we will discuss later on. You can just consider first statement of this paragraph. So the statement says that if there is no resistance or the resistance is negligible, will there be a uniform temperature distribution in the body or not?
There will be uniformity.
Yeah, so it means that if I have a plain slab and my resistivity is zero, which means that my thermal conductivity is going infinity, then there is a no temperature gradient in the x direction. Whatever I have temperature here in the left hand side, I will have the same temperature in right hand side also. So basically T1 equals T2. So there will be uniform heat transfer. There is no temperature change basically. So yeah, this is the basic assumption in the lump system. So we actually in a lumps heat transfer analysis, we assume the body to be in the uniform heat conduction process. So both statements are true here. So we will discuss more about these systems in the subsequent questions. So first, let's finish the fin question here. So this is I think the last question about related to the fin extended surface heat transfer. So the next question is, we have an iron bar with a given thermal conductivity, and we have that iron bar is used for the chimney support to is exposed to the hot gases at 625 Kelvin with associated convective heat transfer coefficient of 740, and the bar is attached to two opposing chimney walls which are at 480 Kelvin. The bar is 1.9 centimeter in diameter and 45 centimeter long, and we need to determine the maximum temperature in the bar. So to determine the maximum temperature in any geometry, whether that is a plane slab or fins or cylindrical or spherical geometry, the basic criteria is to get the temperature profile, to write the temperature profile as a function of x or the spatial parameter, and then to find the slope of this temperature profile, because the maximum temperature is the area where the slope is zero. Like here, this is my maximum temperature, and here my slope will be zero. So first, the basic concept is to find the temperature profile in terms of x, and then take the derivative of that temperature profile and equate it to zero. And from this equation, you can find the location where the temperature profile, where the temperature is maximum. So for example, if my temperature is, let's say, Cx squared plus x, this is my temperature profile. I will take the derivative of it, which is this. Now the slope will be zero at the maximum temperature, which says that, and my value of x will be then minus 1 by 2c. So this will be the location where this temperature profile, the slope of this temperature profile is zero, or the temperature is maximum. So in the question, we already given the temperature profile here. So we just need to put the values in here to find the maximum temperature. So let's find m first. So m square is hp by ka. So I can just put the value of h and k, p and a from the question. So my parameter will be 1.9 10 to the power minus 2. I'm using the SI units, and my thermal conductivity is 55. This is my cross-sectional area. So we have to calculate. After calculation, we will get ms 53.71 meter inverse. So we just need to substitute the values here. So since we need to determine the maximum temperature, we need to take a derivative of this equation and equate it to zero. So the slope should be zero here, which says that. So if I take the derivative, so let me write the equation first. Now taking the derivative with respect to x will give me equals to 0. So this expression become mx equal to 0. So this will just go to 0 at the right hand side. So this is my expression. So the sine hyperbolic x will be 0 at x equal to 0. So which implies that my temperature is maximum at x equal to 0. So we can just put this value of x into our temperature profile to get the maximum temperature. So after calculation, we will get the theta is around 1.6 10 to the power minus 3 something, and T max minus T naught will be 625. So it is 1.6. So this will be my maximum temperature. So here in this question, again, I will revise. So we have given a fin and we have given a temperature profile of a fin, and we have given the thermal conductivity and the heat transfer coefficient, and we have asked to solve for the maximum temperature. So for the maximum temperature, we need to calculate the slope of the temperature profile by taking its derivative with respect to x and equate it to 0. By doing this, we can find the value of x here at where the temperature is maximum. Once we get the x, we just need to put the x in the temperature profile to find the temperature. Any doubt on this question?
No, sir.
So let's move to the next question. So in this one, we need to explain the Biot number. So Biot number is a critical parameter to determine the heat transfer in the lumped system. So basically, for the unsteady heat transfer process, we have to solve this governing equation. But this governing equation is very difficult to solve. We need to use highly advanced mathematical concepts like method of separation and all to solve this governing equation. And even after that, we need to make various assumptions like a long body or semi-infinite body to further get the solution out of it. But otherwise, there is a very simple way to solve the unsteady problem, and in which we actually ignore the time variation of the heat transfer. So we actually ignore the time variation of the heat transfer within the solid body, and we just considered how the heat transfer varies with time in the convection process. So for example, this is my body and there is a fluid here. So assume the fluid is having the temperature T1 and body surface has the temperature T2, and T1 is greater than T2. there will be a convection mode of heat transfer from fluid to body. And when it happens, the temperature T2 will increase. And when the temperature T2 will increase, there will be the conduction heat transfer here inside the body. Now, in the lump system, we assume that the conduction inside the body take place instantaneously. That means the temperature variation with time should be very less, 0. So the variation of temperature in time should be very, very fast. So we cannot actually feel the unsteadiness in the heat transfer inside the body. So the concept is it quickly attain an equilibrium temperature inside the body due to the heat conduction. So we don't need to worry about the unsteady part inside the body, and we can just solve with this assumption. We can just we can actually simplify the transient unsteady heat conduction problem. So for this, we actually define the Biot number, which is the ratio of resistance due to conduction to the resistance due to convection. So now, if my resistance due to conduction is high, it means that the system will take a long time to transfer the temperature, to transfer the heat, because my resistance is more, so there will be more time. So like there will be some significant time to attain the uniform temperature. So this is my uniform temperature. Let's say the green line is the uniform temperature, and it will take a long time to attain this. So this is my initial T1 and T2. So if there is more resistance, which means there is a less thermal conductivity, which means that it will take more time to attain uniform. But if the resistance is very, very less, which means the thermal conductivity is very large, and the system will attain the uniform temperature very quickly. So I can write Biot number also as HL by K. So here is H is the heat transfer coefficient of fluid, and K is the thermal conductivity of body. So for the lumped heat transfer systems, since we are assuming the resistance is negligible, because we want the temperature to attain the uniform temperature as quickly as we can, so my numerator should be very less than my denominator. That means that for the lumped heat transfer, my Biot number should be less than 1 or close to 0. With this assumption, we can use the lumped heat transfer system effectively. On the other hand, if the Biot number is greater than 1, which means that there is a heat transfer from fluid to the body, which takes some time. And inside the body also, there is a conduction process, which will take a significant amount of time to attain the uniform temperature. In those cases, we cannot use the lump heat transfer concept. It will be very ineffective there. So we will use a different mechanism. And some of these mechanisms is to solve the governing equation. Or use the Hazelner chart, or do some correlation, experimental correlation, to determine the thermal conductivity or various properties of the material. So these are some indirect methods. So the first step in the unsteady heat transfer is to solve for a system where Biot number is less than 1. And I think this is the major part of the syllabus in the undergraduate heat transfer also, to consider only the system where the Biot number is less than 1. So any questions related to the BIOT number here?
No, sir.
Okay, so let's solve some question related to the same concept. So the first question is the related to the lumped heat transfer. So the steel balls of 12 mm in diameter are annealed by the heating to 1150 Kelvin and then slowly cooling to 400 Kelvin in the air environment, for which T infinity is 325 Kelvin, and we have given the heat transfer coefficient. Assuming the properties of the steel to be K, 40 watt per meter Kelvin, density is 78000, and the specific heat is 600 joule per kg Kelvin. We need to estimate the time required for the cooling process. So the governing equation we usually solve for the lumped heat transfer process is energy out equals to energy storage. Now, depending upon the question, it can be energy in or energy generation and so on, which is to be equated with the energy storage here. So I will not be deriving the equation for the lumped heat transfer. I will just directly use the formula for the lumped heat transfer. So first, let's check the BIOT number for this problem. So the BIOT number is HL by K, and my heat transfer coefficient is 20. My characteristic length will be R by 3, and my thermal conductivity is 40. So my BIOT number will be 0.001, which is actually perfect to use the lumped heat transfer analysis. So once we got our BIOT number, we can just...
How you have taken LC equal to R by 3?
So this is my characteristic length. So basically my characteristic length would be perimeter by area. So my perimeter would be pi d, and my surface area would be pi by 4 d square. So it will be around 4 by d. And here we have given the steel balls. So for the spherical surface, we can write the perimeter by area. I mean, we can use the same equation. So we will get, so for the spherical case, our characteristic length would be around R d by 6, which is, it will be d by, d by 6. And for the cylinder, I think it is d by 4. And for the slab or for any rectangular geometry, it will be just the dimension, the length dimension of the plain slab.
Okay, sir. Thank you.
So once we get the BIOT number, we can just use the formula here. So we can take a log. So we will get and then we can write time as rho VC HA So this is our expression, and we can put the values here. So density is 7800, and we can write V by A as R by 3. We can write V by A as D by 6. So my diameter will be 12 mm, and my heat capacity is 600, and my heat transfer coefficient is 20 by 6, multiply by 6, and so my initial temperature is given as 1150, and the temperature of the fluid T infinity is 325, and the last temperature of the steel ball is 400. So this Ti is my initial temperature, and the temperature of fluid is 325. So we just need to calculate this expression, and we will get about time as, which is 0.3 hours. So it is just based on the one formula of Lambda heat transfer. So first check the Biot number here. So for Biot number, we need this characteristic length, which this would be area by perimeter inverse. Yeah. So to calculate the characteristic length, we just need to find the ratio of area into the cross-section area into the perimeter, and we will get the characteristic length based on the geometry of the body which is given in the question. So based on this, we will calculate the Biot number and decide whether to use the Lambda heat transfer analysis or to use some other method. So we get the Biot number is less than 1, which is close to 0, and we use the Lambda heat transfer process. For this, we just need to use the formula here. We need to find the temperature here. So we just substitute the value into the expression. So is it fine?
Yes, sir. How to solve this problem if the Ti is equal to T infinity? Because initial temperature can be equal to the air ambient.
Well, in that case, there will be no heat convection. We cannot use the Lambda heat transfer process, because if I have a body and my initial temperature is equals to the fluid temperature, then there is no heat transfer due to convection. There will be heat transfer only through conduction. So it will be just a heat conduction process. So in that case, you can just use the Fourier's law, that's all, because there is no convection heat transfer which will going to happen.
Okay, sir. Thank you.
Yeah. So let's move to the next question. So the next question is the same. Same concept. So we have given the carbon steel shaft of 0.1 mm diameter. 0.1 meter diameter. Our heat treated in a gas-fired furnace whose gases are at 1200 Kelvin and provide a convection coefficient of 100. When the shaft enter a furnace at 300 Kelvin, how long uh, must they remain in the furnace to achieve a center line temperature of 800 Kelvin? So again, we need to check the Biot number here. And for the cylindrical case, we can use the characteristic length as r by 2. So again, for the spherical case, it will be r by 3. For cylindrical case, it will be r by 2. And for the rectangular geometry, it will be just r, or the width of the geometry there. So our Biot number will be 100. So since they have mentioned the grade of the steel, we can use the thermal conductivity or all the property like density, thermal conductivity, specific heat capacity from the handbook. So usually in the question in the semester exams or in the GATE exam, we usually have all the values specified in the question. But in some textbook, they just mention the grade of the metal. So from the handbook, we can just directly look all the properties of that metal. So I will be specifying the property here. So my radius is 0.05 and my thermal conductivity here is 51.2 watt per meter Kelvin. And density is 7832 kg per meter cube, and my specific heat is 541 joule per kg Kelvin. So here the Biot number will be on calculating, we will get the Biot number 0.0488, which ensures that our Biot number is less than 1. So we can use the dumped heat transfer process again. We can write down the same formula. Can take the log so we need to find the temperature here. Sorry, time here. So we just need to substitute the value, and my V by A area will be just D by 4 for the cylindrical case. C is 541 and my heat transfer coefficient is 100 volt. So my initial temperature is 300 and the temperature of the fluid is 1200. And we need to find the temperature when the temperature, we need to find the time when the temperature reach 800 Kelvin. So we just need to calculate the value, and after calculation we will get the time as 8:59 seconds. So again it is a same question. So we just need to first check the Biot number, and after the Biot number we just substitute the formula for the lumped heat transfer to calculate the time or the temperature depending what they ask in the question. So let's move to a bit complicated one. So in this question we have given a tool used for fabricating a semiconductor devices consist of a chuck onto which very thin silicon wafer is placed. We have given the properties of a silicon wafer. Once in position, an electric field chuck is energized, creating an electrostatic force that holds the water wafer firmly to the chuck. To ensure the reproducible thermal contact resistance between the chuck and the wafer from cycle to cycle, pressurized helium gas is introduced at the chuck, radially outward between the asperities. An experiment has been performed under condition for which wafer initially at the uniform temperature 100 degrees Celsius is suddenly placed on a chuck which is at a uniform and constant temperature at 23 degrees Celsius. Okay. With the wafer in place, the electrostatic force and the helium gas flow are applied. After 15 seconds, the temperature of the wafer is determined to be 33 degrees Celsius. So what is the thermal contact resistance? So this is again the unsteady heat transfer problem. So we already given all the temperatures here, and we have given the time, and we need to determine the resistance. So basically our schematic of the problem look like this. So there will be some kind of resistance here, and we need to find this resistance. So there will be some energy stored which is uniformly varying in the geometric direction, and there will be some heat conduction out from this body to the other body. So my governing equation will be now there is no heat input and heat generation, so it will be just E out minus energy storage, and my E out is due to the heat conduction, and this is per unit. I'm writing in terms of per unit area, so I just consider the weight. So this is my equation. So it is always better to start from the governing energy balance equation, because in many questions we have given the radiation heat transfer also. So based on if the energy is incoming to the system or outgoing to the system from the radiation heat transfer or the conduction heat transfer or even from the heat generation, we can analyze from the energy balance, and by using the energy balance we can draft our own differential equation. So the lumped heat transfer process is just a byproduct of this differential equation. So here I can write heat conduction as T difference between the temperature and the resistance, and we need to find this resistance R. This resistance is due to the conduction process. Now we can just integrate this equation 1. So I can move this into the left hand side, and I can move this temperature term along with the dt. So this is just a rearrangement of equation 1 here. Now integrating equation 2, we can just directly write the solution after integration. So this will be minus T R. So this expression is very similar to the lumped heat transfer expression that we used in our previous problem. So we have to find the resistance, so we can take the log. We just need to put the values here. So the time is given at after 15 seconds, and the density is 2700, with is 0.78, 10 to the power minus 3, and the heat capacity is 875. TW is 33. Check temperature is 23. So we just need to calculate the value, and after calculating we will get the resistances. (4.1 10 to the power minus 2 meters per Kelvin per watt). So in this question, we have given the all the temperatures and the time. We have given the initial temperature, surrounding temperature, as well as the temperature at specific time, and we need to find the resistance. So we know that the heat transfer is going to take place through conduction process. So we use the energy balance. We balance the conduction heat transfer with the energy storage, and we find out our own expression, lumped heat transfer expression after integration. And after that, our temperature profile is become a function of the resistance, unlike in the previous question where the temperature profile is a function of heat transfer coefficient. So in this case, the temperature profile is become a function of resistance here, and we need to find this resistance only. So all the other steps is similar to the previous one. We already know the temperatures, we already know the time, and we just use this expression, this solution, to calculate the resistance. And if there was a radiation heat transfer, let's say, so in terms of conduction, we can use the Stephen-Boltzmann law. And we can equate it to energy storage. But since in the radiation process, the temperature are having the fourth power, it is very difficult to calculate the temperature analytically because it has the fourth power in the LHS, and in the RHS we have a differential time dependent temperature. So it becomes very difficult via mathematically, but you can use the numerical techniques to solve with the radiation heat transfer. And all the other things are just straightforward. You just integrate it and find the solution and just substitute the values. So any doubt in this question?
So this radiation mode will be coming in E out?
Yeah, I mean, I'm just considering the different example. Like if there is a radiation heat transfer, in that case, we just need to balance the Stephen-Boltzmann law with the energy storage. As of in this question, there is no radiation heat transfer.
Okay, so if it is there, then it will be in the E out.
Yeah, so then you need to figure out E out and E in. So in this question, the E out was heat conduction. There, as per the question, you need to figure out how the heat coming outside from the system. If it is radiation, then you can use the Stephen-Boltzmann law in the energy balance equation. You can just balance with the energy storage and just integrate and then find the solution after integration.
Okay, sir.
So let's move to the next question here. So the next question is, a person is found dead at 5 p.m. in a room whose temperature is 20 degrees Celsius. The temperature of the room is 20 degrees Celsius. The temperature of the body is measured to be 25 degrees Celsius when found, and the heat transfer coefficient is estimated to be 8 watt per meter square Celsius. Modeling the body as a 30 centimeter diameter, 1.7 long cylinder, estimate the time of death of that person. Okay, it is now figured. So again, we need to check the Biot number, but there is an exception in this question. We will find out that. So I can just directly write the value of Biot number, which is about 0.89. So here in this question, the Biot number is approximately equal to 1, like very close to 1. So the lumped heat transfer process will give the approximate result only because it close to 1. So we can get the time of death, but that will be the approximate time of death. It will be a more probabilistic time of death. So let's use the lumped heat transfer process. We will use the same formula. So it will become so we just put the values here. So the density, so let's say 996, and V by A is, I'm just directly putting here 0.0689. Heat capacity is 4178, and the heat transfer coefficient is 8, and the initial temperature is the human body temperature 37, and the room temperature is 20. And when the body is found, the temperature was 25. So again, just calculating all these things, we will get the time as 43,860 seconds, which is 12 hours. So based on the lumped heat transfer analysis, we can see that we can able to estimate the time of death of the person. Now the Biot number is very close to 1, so this time will be the rough estimate. So we can write in terms of a range like 11 to 13 hours or something. If the Biot number in the same question is very less than 1 or close to 0, the time we will get, this 12 hours time, will be the more accurate. So the range of time is become shortened itself, but the Biot number is depend on the physical property of the body. So it will be a rough estimation of the time. So any doubt?
No, sir.
So let's move to the next question here. So we will solve this question after 11th one. So consider a 1000-watt iron whose base plate is made of 0.5 thick aluminum alloy. The base plate has a surface area. We have given the properties of the aluminum alloy, and the surface area is 0.03 meters square. Initially the iron is in thermal equilibrium with the ambient air at 22 degrees Celsius, and we have given the heat transfer coefficient as 12 watt per meter square, and assuming the 85% of the heat generated is the resistance wire is transferred to the plate, determine how long it will take for the plate temperature to reach 140 degrees Celsius. Is it realistic to assume the plate temperature to be uniform all the times? Now to answer the last part of the question, is it realistic to assume the plate temperature to be uniform all the times? We just need to calculate the Biot number, and we should see that if the Biot number is close to 0, because if it is close to 0, then the resistance will be very less. Resistance due to conduction will be very less, and there will be uniform temperature inside the plate. So let's first calculate the time. Let me use separate space. So this is our energy equation. because there is a energy output from the iron, and there will be some energy incoming also. That is 85% of the heat generated, which is 1000 watt, is transferred to the plate. So plate is getting energy, and it is also releasing energy into the air. So there is energy intake as well as the loss of energy. And now we equate it to energy storage. So energy incoming is 85% of the energy generated, which is 850 watt. And energy, so the iron plate is losing its energy due to the convection, because it's losing the energy into the air. So there will be outgoing heat transfer due to the convection mode. So let me write this Q in, and the Q out will be, so we are just using the Newton's law of cooling. So my heat transfer coefficient is 12. Surface area is 0.03. And the temperature of plate is 140, and the air is 22. So when we solve this, we will get the Q out is 22.2 watt. So now we will use the governing equation. So the governing equation is we can write is Qn, change in time, Q out, change in time, and the energy storage is just mCp delta T. So basically it is Q in, Q out is equal to mCp dt by d small t. So I just put dt here, and I just write the time in terms of a time difference. So my Q in is, so my delta T will be Q in minus Q out and mass is density multiplied by volume Cp delta T Q in minus Q out. My volume will be length multiplied by area. So my mass will be density length multiplied by area, which is 4.15 kg. And my temperature difference is 140 minus 22. My Q in is 850 minus Q out 22.2. So my change in time will be 51.8 seconds. So this is one part of the problem. So the other part is to calculate the Biot number. And when you substitute the value of sorry H and K here. So H is 12 and thermal conductivity is uh, can be determined from the thermal diffusivity. You will get the Biot number at around 10 to the power minus 4. So in that case, the temperature is uniform all the times because my Biot number is close to 0. So in this case, we have given the iron, and we have given there is output of heat and there is an input of heat due to the heat generation. The heat input of heat is just 85% of the total power of the iron, and the output is due to the convection because whatever the heat it will take, it will convect it to the air, and we equate this equation to the energy storage and we calculate the time. So instead of taking using the integration and all, we already find the Q in Q out. So we just write the time in terms of a time difference from initial to final point. You can just consider the initial time as 0. So this delta T will be just the final total time it will take to do all the process like convecting the heat transfer to the air and generate there will be some incoming heat from the power output also. So yeah, any doubt in this question? So
No, sir.
yeah. So let's move to the next question. So in the areas where the air temperature remains below 0 degrees Celsius for a prolonged period of time, the freezing of water in underground pipes is a major concern. Fortunately, the soil remains relatively warm during those periods, and it takes weeks for the sub-freezing temperature to reach the water means in the ground. Thus, the soil effectively serves as an insulation to protect water from sub-freezing temperature in winter. So the ground at particular location is covered with a snowpack, which is the ambient temperature is minus 10 degrees Celsius for a continuous period of 3 months. And the average soil properties at that location is so we have given the thermal conductivity of the soil 0.4 and diffusivity is 0.5 10 to the power minus 6 meters square per second. And assuming an initial uniform temperature of 15 degrees Celsius for the ground, determine the minimum burial depth to prevent the water pipe from freezing. So in this question we have a, let's say, a ground we have given. We have a infinite pipe, and this is the ground. My surface temperature is minus 10 degrees Celsius, and there is a water in the pipe just flowing down. So we will solve this question by not using the lumped heat transfer. We will solve this problem as a long body problem. So usually in the exams, it will be directly given in the question that to solve by lumped heat transfer process or to consider some other situation. So basically you don't need to worry that which method you need to use. For the semester exam, you can always check the BIOT number first to ensure that you have to use the lumped heat transfer process. But in the competitive exam, it is usually always given because it will be a waste of time to check the BIOT number first and then to decide which uh, method is to use. So I will be using directly the long body problem here. So for this, the temperature variation is given as a error function, and we need to define this error function based on the charts. So you can just find the charts in any heat transfer book. So we already have given the all the temperature. So my surface temperature is 0. My initial temperature is plus 15. And my surface temperature is minus 10. So it will give me 0.6 equals error function alpha t. So from the graph, we can actually select the value of this error function. So we can use the graph. So this error function is equals to 0.6 here, which means that we already have this as a 0.6, which we calculate from the temperature variation. And for 0.6, we can approximate the error function close to 0.3 here, 0.36 here. So this is 0.6, and corresponding to the 0.6, my error function from the chart is 0.37. So this value is 0.37 from the chart. And we need to calculate the depth, which is x. So my thermal diffusivity is 0.15, 10 to the power minus 6. Okay. And my time is so here I'm taking a week time. So a week time would be around 10 to the power 6. So this is my rough 1 week time in seconds. So my burial depth should be, after calculating, should be around 0.8 meter. So here we just need to calculate the burial depth, and we use the long body method. So in those cases, my temperature variation is given in terms of the error function x by 2 alpha t. Now by calculating the left hand side, we can write the error function in terms of some numerics, and from the graph, based on this numerics, whatever we are getting from the temperature balance, we can actually just directly look the inside expression of the error function here. Once we get that, then we can either find the depth, thermal diffusivity, or the time based on whatever they ask in the question. So basically, these types of question where the lumped heat transfer analysis is not valid, and where you have to use the semi-infinite body or the long body assumption, the question are very direct. So in those cases, you just need to use the chart and the direct expression from the concept. And basically, if in any case there will be information given about the error function, and if not, then the exam might give some combination of the value of the error function or some small chart like this. Some chart like this they should be given. The competitive exam, they usually give 4 or 5 values of the error function, and from these 4 or 5 values you can easily figure out the expression of error function based on whatever we have calculated. So we calculated 0.6 from the temperature, and we determined the value of error function is 0.36 in this problem. So basically, these types of problems are just a substitution problem, where we just need to put the value of thermal diffusivity, time, or the depth in order to calculate the variables after looking from the charts. So, any doubt in this question?
So, sir, this question has reduced to semi-infinite system because length of the pipe is not given.
Yes. Yeah.
If the length of the pipe would have been given, then it would have been the problem which we have earlier solved. Is it the case?
No. So there are multiple cases actually. So if the length is given and if the Biot number is greater than 1, then again the lumped parameter analysis will not give the accurate result. So in that case, you can directly solve the governing equation, like you can just directly solve the governing equation, but the method of solving is kind of a non-trivial. You have to use the method of separation or the Fourier series, something like that, to solve this equation. Once you get the solution, you need some further assumption to get the solution out of it. So the mathematical part will be a bit complicated. So most of the time we will be just focused either in the lumped heat transfer problem or in the semi-infinite body problem, where you need some indirect mechanism like charts, tables to calculate the error function or some properties of the body. After getting the data from the table, you just substitute the value in the formula, that's all. Otherwise, you can always solve this governing equation. If the dimension of the body is all given and the Biot number is greater than 1. But usually in the undergraduate course, in the exams, this is very unlikely. Like it is always better to study this kind of problem. You can find how to solve such kind of a problem in various mathematics books. I can write here.
Okay, sir.
This is one method to solve this kind of equation. Not only this, like based on temperature, even any dependent variable. Let's say you put y in terms of t, so it will be just dy square d square dy by dt, something like that. And you can use some Fourier or Laplace method to get the solution out of it. So you will be getting the solution on the temperature in terms of time. So the solution will be looking very complicated. So the temperature will be some sine cosine function of the space, and you need further assumption to solve the temperature in terms of space. You can check that if you want. But in all the cases, I think these two problems are self-sufficient, like learned heat parameter and this semi-infinite body. So any doubt until now in any question?
No, sir.
Okay, so in case you have any issue, you can just check the YouTube. I will upload this video in YouTube, and I will also I upload this PDF in the Google Drive. So I think you can already access the YouTube and Drive link, right?
Okay, sir.
Yeah. Okay, then next week we will be solving more question based on this on steady heat transfer, and probably we will look some heat convection problem also.
Okay, sir. Sir, but only that the problem is that we didn't get the message. Only I just casually clicked the previous links and then I joined because earlier we were getting the messages early in the morning. Today we have not got the message of your class.
Okay, so if next week you didn't get the message, you can just mail me. So I'm writing my email ID here. Just a minute. So this is my email ID. In case if you didn't get any mail from NPTEL by let's say 11 a.m. or 12 a.m. next week, you can just inform me. I will inform the NPTEL about this.
I have not got the mail. Where you have written, sir?
I actually written in the chat my email ID because I got the mail from NPTEL yesterday itself that we have a class today. So I thought that people will receive it, but yeah.
Okay.
Let me write here also.
Yeah. If you can write it here, then.
This is my email ID. You just can inform.
Sir, after D, it is O or 0?
Just a minute. It's a 0.
Okay. Okay, sir.